All right, welcome to week 5 of Honors Physics e-learning. This week, you will be able to analyze an object in equilibrium, and you will be conducting an experiment at home to determine the static coefficient of friction between various surfaces. All right, first off, you'll be going through this slides document with the notes that has our week 5 learning targets and success checklist. You should be able to explain what equilibrium means, give examples of an object in equilibrium that is both stationary or moving. If an object is not in equilibrium, you should be able to calculate its acceleration. Lastly, after doing the week 5 practice Google form and the week 5 project, you should be able to draw a force body diagram for an object sitting motionless on an angled ramp. And lastly, be able to determine that static coefficient of friction from that particular setup. A little background here, right? Newton's second law. We have to define what net force means. Net force is the sum of all forces applied to an object. If you want to practice this, all right, click this little challenge thing. You'll have a minute to get as many correct as possible. Just remind you what net force means. In the examples to the right, if forces are in the same direction, you can simply add them together to get the net. If they are in opposite directions, you can subtract them to get the net force. Okay. F net equals ma is Newton's second law. Notice that the two of these are bold-faced to represent that they are vectors. Mass, on the other hand, is just a scalar. So in whatever direction your net force points, your object will accelerate that way. There's another little interactive one-dimensional Newton's second law problem. Will help you review how to apply Newton's second law. Just try it once. We're going to extend ourselves from what we've learned previously, though. If the sum of the forces in both the x and the y directions are non-zero, then we're going to have to combine those force components just like we did with velocity vectors in the projectile unit. So in this example here, we have a force in the y direction of 30 newtons and the x of 40, right? We can use Pythagorean theorem to get the magnitude of the net force vector, right? In this case, we would get exactly 50 newtons. And we could also define the angle at which this net force points by using the inverse trig functions, specifically inverse tangent here, where you use the y component of force over the x component. In this example, we get an angle of about 37 degrees, which makes sense because the y force is a little less than the x, leading to an angle less than 45 degrees. Now, the state of equilibrium occurs whenever an object's net force is equal to 0. So when you sum up all the forces acting upon the object, if they all balance out, that will imply that the object is not accelerating, right? So if your net force is 0, the acceleration of the object must also be 0. This is demonstrated in the little figure to the right here. All 5 of these forces, if you sum them up in the y direction, they balance, as well as the x direction. Now, with an object being in equilibrium, that does not mean that it has to be at rest. Okay, now that is one type of equilibrium referred to as static equilibrium, right? Object at rest, remaining at rest. However, an object can be moving yet be in equilibrium, right? And this is referred to as dynamic equilibrium. This is when an object does not accelerate, but does just maintain a constant non-zero velocity. Some examples of static equilibrium: simply an object resting on a table, a bridge structure that's at rest, remaining at rest. Some examples of dynamic equilibrium, though: a hockey puck sliding along ice at a constant velocity, or a skydiver falling at terminal velocity, meaning that the skydiver no longer is picking up speed as it falls, right? This occurs when the air resistance force cancels out the force of gravity tugging the skydiver downward. Quick review on frictional forces heading into this activity. Right, remember friction, you can have either a static frictional force or a kinetic frictional force. Static frictional forces are variable. They can be from slightly above zero all the way up to a maximum value, and that maximum value is equal to its coefficient of static friction multiplied by the normal force, which is the force pushing on the object from the surface beneath it. Right? Kinetic friction can only be a singular value. It's equal to its kinetic coefficient of friction multiplied by that normal force. Right? Frictional forces will always point in a direction opposite the object's velocity or intended velocity. What that means is, say in this picture, if I'm trying to push this object to the right, the static frictional force will point to the left because it's counteracting the intended velocity of the person trying to push it forward. Right? Now remember, this symbol is the Greek symbol mu. It represents coefficient of friction. The bigger this value is, that means the rougher the two surfaces that are in contact. Ideally, if you had a frictionless surface, mu, or the coefficient of friction, would be equal to exactly 0. All right. If you want to remind yourself of the friction lab we did earlier in the year, that is linked at the bottom right-hand corner of this slide. Now we're going to specifically look at an object maintaining itself at rest on a ramp. Okay, now if you were to put an object on a ramp and angle it upwards, if it does not slide down, that means there is enough static frictional force to keep it still. Right? If you had a frictionless surface, the moment you pitch the incline up at any angle, the object would slide down immediately. Right? Now, if we analyze the forces that are involved here, you have three. You have the force of gravity pulling the object downward. You have a normal force beneath the object pushing up, right, from the surface. And then you also have static friction. Now, if an object is in equilibrium, all three of these forces will balance out to 0. Now, the best way to visualize this is this little movie to the side here that I'm going to play here. Notice these forces are color coded, right? The normal force always points perpendicular from the surface. The blue weight force vector always points directly down, and the green static frictional force always is pulling up the ramp because the intended velocity is for this to slide down the ramp. Now, I paused it here for a moment to point out a few things. We are going to maintain our y-axis being perpendicular to the ramp and our x-axis being along the ramp. This allows us to only break up one force into its components, and that would be the weight vector. So notice there are two arrows drawn here to represent the component of the weight that is parallel to the ramp, as well as perpendicular to the ramp. Now, if this thing is in equilibrium, these two forces should balance out. So our normal force will be equal to the perpendicular component of the weight, while the parallel part of the weight will equal or balance out the static frictional force pulling up the ramp. That leads this to equilibrium. If I continue to play this, you will notice that as this force gets bigger, that one gets bigger. As this one gets smaller, that one gets smaller. Your normal force is just the force from the ramp pushing up. It's only going to push whatever it needs to counteract the other, downward force. So as an example with some numbers, right? If we had an object that was a half a kilogram, right? Acceleration due to gravity is 9.8 meters per second squared. Say we had a static coefficient of 0.4 and we pitch this thing up at a 14-degree angle. Now, this thing is interactive here. If you click this, you can actually run this lab and kind of mess around with it. So if we run through this, that means our force of gravity or weight is 4.9 newtons. If we multiply by the cosine of an angle or the sine of the angle, you can kind of draw this triangle out and prove that using the cosine, we'll find this perpendicular piece. The sine will find the parallel piece. Notice with this little 14-degree angle, most of the force is into the ramp. Notice it's 4.75 newtons. But there's a 1.19 Newton force that's trying to pull this down the ramp. Okay. Now, if there's enough friction here to balance out that 1.19 newtons, this object will remain still, all right, and not slide down the hill. All right. So we make this assumption here, and it's not really an assumption. This is what they would balance. The normal force would be 4.75 newtons. We need that because we can check if we have enough friction, right? Because remember, if you take mu sub s and multiply it by the normal, which is not exactly equal to the weight here, it's only 4.75 newtons, we can calculate that we have 1.9 newtons of available static frictional force. But we only need 1.19 to balance out the weight down the hill, so this thing's not going to budge, right? If we kept pitching the angle up more, even above 14 degrees, as long as we were under 1.9, this thing will not move. The moment we exceed 1.9, though, is when the object will now start to slide down the hill. So the experiment you are going to run at home, you're going to just try to get a few random objects. Possibly you could take a piece of wood as a ramp or anything that's kind of sitting around the house, and you're going to go through various surface interactions and figure out their mu sub s. Now, you can do this without even measuring the mass of the object. Some of you probably don't have mass scales at home. The only thing you need to do here is measure angle, and your directions in the lab will tell you how to do that. Okay, so if we had an unknown mass, we know the acceleration due to gravity. Our coefficient of friction is unknown. The only thing we're going to do is measure the angle. We can do some nice little algebraic magic here to find the coefficient of friction. All right, so if you look at this, right, and we do some math, this force of gravity that's perpendicular, right, to the ramp, which is mg times the cosine of the angle, will be equal to the normal force. All right, so that's what's represented right here, okay, in this section. Now, if we look in the parallel part to the ramp, right, this mg sine of theta, right here, say we find 22 degrees is when this thing starts to go down the ramp, that's going to be equal to your maximum static frictional force, because that's the point where it's just about to go over, right? So we have mu sub s times the normal is equal to this. Now, we can do a little bit of algebraic substitution here, all right? So we have mu sub s, but the normal force, right here, is equal to mg times the cosine of the angle. So I just rewrote that here. And now I get this equation where I know everything, okay? Now, we do know g is 9.8 meters per second squared, but notice it really doesn't matter because we have mg on each side of the equation. If we divide by the weight, right, mg, both of these will cancel out. And you will just be left with a very simple expression where the coefficient of friction equals the sine of the angle divided by the cosine of the angle. And if you have done any trig, you may or may not know this at this point, but sine over cosine is exactly equal to the tangent of that angle. So in this case, if we put the tangent of 22 degrees into our calculators, we get 0.404 out, which would be our coefficient of static friction from this experiment. Good luck with the project.